Okay. All right, good. So let me remind you, okay, let's start off by outlining what it is I want to cover today. So again, just to remind you, the philosophy and the way we're going to approach this subject is I want to start off with things that you're already familiar with, things that you know, and the things that you know are vectors and vector spaces. So we're going to talk about vectors, vector spaces, covectors, inner products on those vector spaces, which will naturally introduce the idea of a metric, which in the next lecture I'll tell you is actually a metric tensor, and I'll define what that means. So I want to cover vectors and covectors today, inner products and bilinear forms, and the metric and its properties. So just by way of recalling what it is we did the last time, we said that if I've got a vector space, let's say V, and that vector space is defined over the field of real numbers. So that is to say, I can take vectors in this vector space and I can combine them by adding the vectors, and the coefficients in those combinations are real numbers. So that's what I'm going to mean by a vector space defined over the field of reals. Vector spaces come with bases. I'll assume that all the things that you need to do with the basis, like make it an orthonormal basis set, holds. So suppose I have two bases. Sorry. Suppose I have two bases, E mu and E mu prime. Say n equals 1 to n. So I'm assuming that I'm working in a n-dimensional vector space. So if E mu and E mu prime are two different bases, different sets of bases for the vector space, then I can expand the one basis in terms of the other. And I'm going to denote this expansion as follows. I'll say that E mu is A nu mu E nu. And I said the last time that I'm using Einstein's summation convention, which says that every time I see an index that's repeated once, one is a superscript, one is a subscript, so upstairs and downstairs, then this implicitly means the same thing as if I had said the sum over nu equals 1 to n, A nu mu, E nu prime, like that. Okay, so I'm just dropping that explicit sum by recognizing that anytime I see such a repeated index, I'm going to sum over it. One thing to keep in mind, in the same way that in a sum like this variable nu here is a dummy variable. You're summing it out. It's like, you know, the integration variable in an integral, you integrate it out. So whatever comes out of it doesn't have any new dependence. You'll see that there's no new dependence on the left-hand side. That's because the new variable here is summed over. It's a dummy variable. It also means that I can change it to whatever the hell I want to call it, right? Mu, not mu, nu, alpha, beta, etc. The mu, on the other hand, is a free variable, which means I get to pick what it is, but it's not being summed over. Okay, so it's important to distinguish between a free variable and a dummy variable. The dummy variable is summed over, and the free variable, you're allowed to pick 0, 1, 2, 3, or in this case, 1, 2, 3, through to n. This equation here on the left-hand side is technically a matrix equation, right? I would otherwise write it as in the form E mu vector is some matrix, call it A, E nu, sorry, let me take the components out. I would write it as E, the vector E is A times the vector E prime, where I mean by the right-hand side, I mean a matrix product, okay? So the matrix capital A has components A, mu, nu, okay? And it's important to recognize that it's a matrix here because its components are indexed by two numbers, mu and nu. So A11, A12, A13, etc. are organized in this matrix capital A. Is that clear to everybody? Thumbs up in the reactions will suffice. Okay, so given that I can think of this thing as a matrix equation, I can also invert this matrix equation and write E prime then as A inverse E. And that's literally all that this equation is telling us. It's saying that I'm inverting this equation by multiplying from the left and the right with the inverse of the matrix A. The matrix A as a transformation of bases is an invertible matrix. Its inverse is denoted by A inverse, and the components are denoted by A inverse mu nu. So this equation here on the right-hand side is nothing but the component form of this matrix equation here. Again, everybody with me? Right. Okay, so that's what we did the last time. It wasn't a hell of a lot because most of last time was spent talking about the logistics of the course. So today I want to start with some of the real meat of the course. Right, the first thing is, if I know how a basis transforms, that allows me to deduce how the components of any vector in that space transforms. For example, if I have two vectors, let's say, suppose I have a vector and I'm going to call it X. I'm going to start by using the notation that you're familiar with arrows and things like that, until we get to the point where we're dealing more with vectors and tensors than anything else, and we're already familiar with these concepts. And then I'm going to drop the arrow with the recognition that what the object is will be clear from the context. But for the moment, since we're talking about vector spaces, I want to treat everything in the way that you're probably familiar with, which is objects with arrows over them we'll call vectors. Okay, so suppose I have some vector like this, X, and X lives in the vector space V, right? And X has components, X mu and X mu prime, in the basis E and E prime, respectively. And so if X living in V has components X mu and X mu prime in the E and E prime basis, respectively. Then the following is true. We know that the fact that X has components X mu in the E mu basis, and I can expand the E mu basis the fact that X has components X mu and X mu prime in the E and E prime basis means the following. It means that X can be expanded as X mu E mu, but it can also be expanded as X mu prime E mu prime, right? They give you the same vector, just with different components in a different basis. Okay, the components of a vector are basis dependent. But I also know that I can expand the basis, the E prime basis, in terms of the E's, and conversely, right? So in fact, let me do it this way. Let's say the primes are here, but this is the same as X mu E mu. Okay, I haven't done anything deep here. I've just changed the order in which I did it. And now I'm going to expand the E mu in terms of the E prime using this equation here. So I'm going to substitute back into here. So this is just X mu times A mu nu E nu prime from equation 1. Okay. So let's call this equation 2. and we're going to need it again. In other words, under the transformation that takes the E mu basis to the E mu prime basis, the components of the vector transform as x mu going to x mu prime equal to a mu nu x nu, just by reading off from equation 2. So notice the following. See how the basis transforms? So the basis transformed like this. The non-primed version transformed, the non-primed version written in terms of the primed version involved A. The primed version written in terms of the non-primed version involved A inverse. But if I go to what we just derived here, the primed version, again, the primed version is related to the non-primed version by A and not A inverse. Sorry, I know there's a lot of back and forth between boards here, but is everybody with me? Anybody with me?
Yes.
Okay. So the components of the vector transform in the opposite way to the basis vectors. Another way of saying the same thing is in the contravariant way to the basis vectors. So if you've done GR in the past, maybe the third year course last year, then you would have heard about these things like contravariant and covariant vectors. And really all it means is that something transforms the same way that a basis transforms or in the opposite way from the way the basis transforms. So let me say that one more time. I make a change of bases to go from non-primed to primed, right? So the E mu, I'm expanding the E mu's in terms of the E mu primes. They expand with the matrix A. If I invert this relation, I can write the primed basis in terms of the non-primed basis, but it comes with the inverse of the matrix A. So that's how the basis vectors transform. Is everybody with me? Yeah? So given that this is how the basis vectors transform, the components of a vector transforms in the opposite way to the way the basis transforms. So in terms of the components, the primed version is written in terms of the non-primed version, not with A inverse, but with A itself. So because they transform, because the components transform with the opposite, transform in the opposite way to the basis, we say that the components of a vector are contravariant. Okay, that's just a little bit of terminology. Now, already in your second year introduction to linear algebra, for example, you would have learned that to each vector space, I can associate a dual vector space. And the dual vector space consists of covectors, and these covectors are really just a fancy way of saying a linear map from the vector space to the reals, if my vector space is defined over the reals. So associated to the vector space V is a space of covectors which I'm going to call V star, again, just following on the notation that you're probably familiar with from linear algebra. And V star consists of linear maps let's call them F, that take V to R. So again, if you remember what you did when you learned about covector spaces and the dual space to a vector space, given a vector space, so given some vector in the vector space, I could find an object, which was the dual vector or covector, such that when I paired these two things up, they gave me a real number. Okay, so that object that gets paired with the vector is a linear map from the vector space to the reals, in the sense that if I have some object that lives in the vector space, in the covector space, call it F. So if this guy lives in V star and X lives in V, then the following is true. F acts on X to give me a real number. What is that real number? Well, F acts on X, and I know that I can expand X in its components in, let's say, the E mu basis. So I can write X like that. The linear map of covectors doesn't act on the components. It only acts on the vectors. And the vectors in any vector expansion are the basis vectors. So what that means is, and because this is a linear map, I can pull out the U's, the X mu's, and the F acts simply on the basis vectors E mu. This guy here defines for me the components of, this guy here defines for me the components of the linear map, the covector. So this is the component let's call it a covector. Notice the following. The covector's components, unlike the vector's components, has a mu, but as a subscript. So the mu is downstairs instead of upstairs. That's important. And everybody see the bottom of this page. It says if F is in V star and X is in V. Chwazi, can you see it now?
Oh, yes, I can see it now. Thank you.
Okay. Can I move on to the next page, or are you still copying it down?
I'm done. Thank you.
Okay. So the things to notice here are the following. The components of the covector have a subscript instead of a superscript, right? So the mu is downstairs. This kind of makes sense because in the expression here, the only index mu occurs downstairs anyway. So we need to be consistent with that. If the index occurs downstairs there, it ought to occur downstairs here. This, by the way, is a definition of what f mu is. So the components of the covector is what you get if you take the linear map and act on the basis vectors one at a time. So f1 would be f acting on e1, f2 would be f acting on e2, etc. Okay? Second thing to note is because now the mu, there's one mu upstairs and one mu downstairs, the instruction following Einstein is that we have to sum over the range of the mu's. So this expression here is actually the same thing as x1, f1 plus x2, f2, etc., right? Going up to the range of the index mu. But what that means is that this is no longer a vector. Because I'm multiplying and adding these things together, it's just a number. This is in fact a real number. This is what I mean by f acting on x gives you a real number. F maps vectors in V to the real numbers. Okay? This is an important point that will become more important as we deal with higher objects like tensors. So it's important that you understand what it is we're saying here. So let's ask then, how do these components of the covector transform? So let's make the same basis change that we started off with. So the basis change 1. Again, recall how things works. The non-primed is expressed in terms of the primed basis by the matrix A. The primed basis is expressed in terms of the non-primed basis by the matrix A inverse. So keep that in mind. And everything that we're talking about, all the transformations are defined with respect to the transformation 1 here. Okay, so let's suppose we make a transformation of basis from E mu to E mu prime, as in the equation that we wrote down earlier. What happens to the covector components? So under the transformation equation 1, f mu, which you'll recall we just defined as the action of f on the basis vectors E mu, is f acting on, now expressing the E mu in terms of the E mu prime. That's E mu nu, E nu prime, like such. Again, f is a linear map, which means that all of these things, which means that it only acts on vectors. And the only vectors in the brackets there are the basis vectors. So I can pull out I can pull these guys out. And that's just A mu nu, F acting on E nu prime. But this is just the components of F in the primed basis. So that's A mu nu, F prime nu. So now we know how the components of the covector transform. The unprimed components are expressed in terms of the primed components by the matrix A, not A inverse. Okay. Again, the unprimed is expressed in terms of the primed like this and not like this. So the components of a vector transformed like this. The components of a covector transform exactly the same way as the basis vectors. And if the other set was called contravariant, the components of a covector transform in the same way as the basis, what we call covariantly. Again, if you've done GR maybe last year or so, you will have encountered these terms like covariant and contravariant. They should have been explained to you, but if they weren't, this is why they're called covariant and contravariant. So physicists will typically say things like the elements of the vector space are contravariant vectors and the elements of a covector space are covariant vectors. Mathematicians think that physicists are weird because this is just a matter of convenience, because V and V star are dual to each other. So what you choose to call co and contravariant is just a matter of convention. Okay, so it's not a big deal. There's nothing deep about it. It's a convention, and we'll agree to stick with this particular convention. Okay, any questions? Another way of thinking of the action of F on X, where F lives in the covector space and X lives in the vector space, is to write it as a pairing. So we will sometimes denote F of X as being identical to F paired with X in this way. Okay. So I know I've written it in a way that's kind of suggestive of an inner product, but it's not an inner product. And it's not an inner product because when you have an inner product between two things, they need to live in the same space. So when you do an inner product, you do a dot product between two vectors, those two vectors live in the same vector space. Okay. These guys do not live in the same space. One is a vector, one is a covector. They live in a dual space. Let me do an example to illustrate where some of you may have seen this before. So an example of this kind of pairing between vectors and covectors is provided by the space of displacement vectors and the space of wave numbers. So an example of this kind of pairing is the space of displacement vectors X and wave numbers which physicists tend to call K. Okay. So these objects, displacements and wave numbers, so physicists call K, mathematicians taking Fourier transforms would call it P. But the point here is that these objects live in different spaces. They're different objects, right? They have different units even. We tend to measure X in, let's say, meters, so lengths. And wave numbers, K, are measured in inverse meters or inverse lengths. So it doesn't make sense to talk about, for example, the vector X plus the vector K. So since these live in different spaces, things like X plus K do not make any sense. Right. However, you know, if you've done any wave mechanics or if you've done anything involving Fourier transforms, then you will see expressions like the following. So in expressions such as psi of x equal to e to the ik dot x, which, if you've done anything involving Fourier transforms, you would know that this is what's called the kernel of a Fourier transform. If you're a physicist, you would call this a plane wave. Either way, you get this object that looks like k dot x in it, right? And one generally takes this to mean k1 x1 plus k2 x2, etc. But this is not a real dot product. In fact, it cannot be a real dot product because that would require the vectors live in the same space. So in this case, this here is not a real dot product. What it does mean a dot x here is just shorthand notation and slightly abusive notation for the statement x mu k mu, meaning that x here is a vector and k is a covector. Right? Again, this is just the statement that x1 k1 must be added to x2 k2, and in 3 dimensions this sum goes up to that. Okay, is everybody clear with this? Okay. Again, I emphasize here that this is just a choice that we make to have x live in V because, x is displacements. Displacements are real things that we can experience. And so we take this to be the real space, V. Whereas the wave numbers are things that live in the more abstract dual vector space to x. Just a convention. Okay. Nothing particularly deep about the choice that we make there. They are dual to each other. Okay. Most of the vector spaces that we're working with, that we will have chance to work with, will come equipped with an inner product. An inner product is just a bilinear form that maps 2 copies of the vector space to the reals. So come with an inner product. Which is a bilinear form. Let's call it G, and G takes V times V to the reals. This V times V here is a Cartesian product, so it's 2 copies of V, and what it means is that G has 2 arguments. Okay, so what this will mean is that I can use it to calculate, for example, the length of a vector. So the length of vector x, for example, is given by the square root of g acting on x and x. Okay. The inner product naturally induces a metric on the vector space. So the vector space is then a metric space. And we can calculate the metric components by looking at the action of G on the basis vectors. So the inner product induces a metric on the space. The components of this metric, the metric components are given by the set of numbers G mu nu, defined by the action of G on the basis vectors E mu and E nu. Okay. So this is important, and the structure of this particular bilinear form is quite central to our story, and we'll return to it a little bit when we define tensors. But first, let me finish off here by just talking about some of the properties of the metric, and this will be useful for what follows. So given two vectors, let's say x and y, we can define the inner product, the actual inner product that pairs x and y to give you a real number, now that we have a metric on the space, as follows. Given x equal to x mu, e mu, and y equal to y mu, e mu. We can define x inner product y to be G acting on x and y, which is, since G only acts on the vectors themselves and not the components, x mu, y nu, G acting on e mu, e nu, which by our recent definition is just G mu nu. That's G mu nu, x mu, y nu. Okay. The inner product has the following properties. Is everybody happy with this? Can I change this? Can I go to a different page? Is anybody still copying anything down? I'm seeing thumbs up, so I'm just going to go. Okay. The inner product has the following properties. First is that since it is a real valued inner product, it is symmetric. in the sense that G of x, y is the same as G of y, x. Which necessarily means that the components G mu nu and G nu mu must be the same. The inner product is non-degenerate, which means that as a matrix, G mu nu has an inverse. And the inverse is denoted by G mu nu with the index upstairs. And it is really an honest-to-God matrix inverse of the problem. So since the inner product is non-degenerate, so G mu nu is invertible. It's invertible in the matrix sense, and it has its inverse, which we'll call G mu nu upstairs, and they satisfy that G mu nu, G nu lambda, again, nu here is a repeated index, one upstairs, one downstairs, which means we're summing over it. It also means that whatever this index, whatever this expression is, it doesn't have any news in it. And this is the same as G lambda nu, G nu mu. So this is just saying that the left inverse and the right inverse are the same thing. And this is mu lambda. This again being the Kronecker delta. This is the components of the identity matrix. So this here is the component form of the statement that G inverse is G inverse G, and both of them are the identity. Okay. This additional structure that the metric gives us allows us to identify V and V star, in the sense that if given some covector F that lives in V star, I can always find a vector in V, let's call that F tilde, such that F of X is the same as F tilde paired with X. Let's write that down because that was a bit of a mouthful. So given F in V star and X in V, we can always find some F tilde in V such that F acting on X is the same as F tilde paired with X in the inner product. What does this mean? It means that F mu x mu, remember this is just what this left-hand side is. Sorry, mu is equal to g mu nu f tilde nu x nu, because that's just what the right-hand side is. But this means necessarily that f mu is g mu nu f tilde nu, because I can change indices, and I should not have this. That's a mu, like such, right? So just identifying the coefficients of x mu on both the left-hand side and the right-hand side. But I can also invert this relation and then write down f tilde of mu equal to g mu nu upstairs, f nu downstairs. So again, given some covector f and a vector x, any vector x in the vector space V, I can use the inner product, this inner product, to find some element of V such that f can be expressed in terms of such that f tilde can be expressed in terms of f in this way. So given this, we can now identify f and f tilde. So in future, when I write things like this, I won't write down a tilde over the f. And subsequently, I can make an identification between between v and v tilde. So we say that the covariant and contravariant components are related by raising or lowering the index. So we relate the covariant and contravariant components by raising and lowering indices with the metric in the following way. So given some f nu, if I multiply it with g mu nu inverse, then the result is f mu with a mu upstairs. And starting off with some f nu upstairs, if I multiply with g mu nu downstairs, that gives me an f mu with the mu downstairs. Is that clear? Okay, so this is how we raise and lower indices using the metric, and this is why we raise and lower indices using the metric, if you've encountered this already from GR. Okay, one point I'd like you to notice is that this identification between the vector space and its dual is a metric-dependent statement. Okay, it really does depend on what choice of metric you have. So this is not a metric independent statement. It does depend on what your G mu nu is. So for example, if we were to restrict our attention to the vector space R to the n with the standard inner product being the dot product in R to the n, then everything that I've just been saying reduces to the standard things that you're already familiar with from doing dot products in R to the n, or in particular R cubed. Right, and the metric on the space reduces to the standard delta mu nu on the space. Any questions? Okay, so that's all I wanted to say today. Let me stop sharing and stop the recording.